Welcome back, students. Now let's do the same problem again, this time using what I call hybrid method. Kind of combining critical value method and probability method together. And this one also goes a little bit deeper in theory. And the advantage of it is, of course, it explains why this method applies in a little bit more explicit way, but the trade-off is a little bit harder to follow. Okay, here we go. Do you drink the recommended amount of water each day? Most Americans don't. Americans drink 4.68 ounce servings of water each day. A sample of 42 education professionals was selected randomly, and the water consumption for 24-hour period was monitored. The mean amount consumption was 39.3 ounces. Assuming the amount of water consumed daily by adults is normally distributed and the standard deviation is 11.2, is there sufficient evidence to show that education professionals consume, on average, more water daily than the national average? Use alpha value as 0.35. Okay, the same problem and same hypothesis. Now let's go over to the method directly. Standard normal picture. Now this one is related to standard normal, not just normal picture, because we are doing transformation and taking z-scores for both cases. Here is the normal curve, and this is standard normal curve, so standard at the origin, so this is 0 in the middle. So I didn't really specify it, didn't need to, because this is 0, and we have to find out the threshold value or critical value of z, or critical z-score, I have to say. And that critical z-score is associated to the alpha value here, which is given as 0.05. Consequently, the left-hand spot is 0.95. Now, what do we do next? You just find out this critical z-score, and we calculate z-score for the given problem here. So z is n minus center over SC, but as a matter of fact, this time this is not going to be the end of this picture. We're going to just use x bar here, and then the center will be mu 0, and then standard error down here is gonna be, of course, sigma over square root of n, and that is a z-score for the mean, so let's name it as z bar. Let me expand the font even further. You can calculate this one explicitly. It's gonna be what? 39.3. Read the problem carefully. X bar is 39.3, and center is 36.8, which is 4.68 ounce servings, and the standard error is 11.2, the standard deviation, over square root of 42, the sample size, and you can explicitly calculate this quantity by punching into calculator. Turns out it is about 1.44 something. And what do we do next? We compare this z bar value and this critical z value. Compare those two, and if z bar falls into blue region, then null hypothesis wins. If z bar falls to red region, alternative hypothesis wins. The conclusion part is kind of similar to the critical value method that we studied, but here we take the z transformations for both cases. Basically, we have one normal curve centered around mu0 and transform it over to standard normal centered around 0. And I just drew standard normal picture here. In chapter 6, I used to draw both pictures and show you the transformation. And we did that, and I assume everybody remembers, or at least everybody knows where to go back and check. So I'll just show you the standard normal picture. And that's how z bar and this critical z are related. And this is the essence of hybrid method. I call it hybrid because this is a computation we used for methods to the probability value approach. But instead of going over to p-value for that, we find out the critical z-score for this one as well, and then compare. The latter part resembles the critical value approach, so it's kind of hybrid. In order to use this method, you have to know the idea of this transformation, the z transformation, and that can be a little bit difficult and confusing, but if you know how to use this and if you're comfortable with it, go ahead and use it. We have z equals to 1.645 approximately. That's coming from that 95% and 5%. This one comes from the computation. And compare those two. So mu0 became 0, so that's 0. And then that critical value x became now critical z-score of 1.644 something. And then finally z bar, x bar became z bar. And it turns out 1.44 something. Compare the z bar and the critical z, and z bar fell into the blue region, so H0 wins. Reject the null hypothesis and reject the alternative hypothesis and accept the null hypothesis. Do you like this method? And I do like this method, but that's because I'm really comfortable with the transformation. But I've seen some students who had hard time understanding this, and also I saw a number of students who felt really at home with this method and used it all the time. Anyway, here is another method that you can use. I didn't specify it as required part for this exercise set, but if you feel more comfortable with the hybrid method, and if you want to stick to this for the rest of the semester, go ahead. Finally, confidence interval method. And I give you this method with a bit of reserve. It may be a little bit confusing, number one. Number two, it does not work for proportion very well unless it is further adjusted. The method is basically finding out confidence interval, typically one-sided confidence interval, and whether mu0 goes to that confidence interval or not. The same situation and same hypothesis. And what do? We just find out confidence interval based upon this. This is x bar, observed mean. So this will give you a confidence interval or confidence bound, lower confidence bound, and one-sided confidence interval, like this. 39.3 is something we found out from the sample study. And if you find out confidence interval, one-sided confidence interval with lower confidence bound, this is what it looked like. Find out confidence interval x1 here, and then compare that with mu0. If mu0 falls into blue region, what does that mean? Mu0 and this x bar are pretty close. Null and this observed mean are pretty close. Null hypothesis wins. If mu0 falls into red region, the null and this observed mean are far away. So null is probably wrong, so we reject null and go with alternative. Alright, this is exactly exactly the same as finding the confidence bound and one-sided confidence interval. What we do this computation. Okay, n minus center over SE. We do that computation and then look up appropriate z-score from the table. This is 5% to the left-hand side. Look up 5% from there. You're going to get negative 1.645. See? These two. Push between these two. Negative 1.64 and negative 1.65. So somewhere in between, negative 1.645. Now solving this equation with respect to x. Here we go. Flip the denominator and then flip the mean to the other side. You end up with 36 point something. This lower confidence bound is 36.45 something, and therefore the confidence interval, one-sided confidence interval, start from 36.45 all the way toward infinity. So whether mu0 falls into this confidence interval, the blue interval, or the red region, is the question that you have to answer as a conclusion. Here is the conclusion, by the way. Oops, what did I do? Yes, okay. Mu0 of 36.8 fell inside the confidence interval, the one-sided confidence interval. So the conclusion, mu0 and x bar are pretty close to each other. Null hypothesis wins. So we reject alternative hypothesis. Or we can say fail to reject null hypothesis. If this 36.8 fell into this red region, then we will reject the null hypothesis, because null 36.8 and alternative 39.3, did I say alternative? Excuse me, observed mean, those two are too far away, so null loses. You go with alternative. So this is confidence interval method, and if you are good at using confidence interval, you can use this method too, but I recommend it only with some reserve, and it is better not to use this. The reason I told you is for small number of students who want to teach this. You really have to know the theory behind all this. What's the difference between confidence interval, that idea, and hypothesis testing, that idea? Or what are the similarities between those? Here we have explicit relationship between one and the other. So for theory this is very good, but that's for 3000 level math. Now problems 3 and 4, I'll just leave them to students. You can do exactly the same as problem number 1 for different numbers, then you get problem 3. Do exactly the same as problem number 2, use probability value method for this setting, you get problem 4. These two problems are left to the students.